Yes, sir.
Great. So distinguish between an oxidizing and a reducing agent in terms of electron gain or loss. Let's do the notes first, the notes bits of it. So redox, redox, R-E-D-O-X, really stands for reduction oxidation. Those two words come together and you get redox. Now, reduction oxidation, you have to define certain things first. What do we mean by reduction? What do we mean by oxidation? Reduction of a species, you're saying something?
No, sir.
Okay, reduction of a species means that the species has lost hydrogen, no, gained hydrogen, lost oxygen, has a decrease in oxidation number, or it has gained electrons. And of course, oxidation is the opposite of that. Oxidation is the gain of oxygen, loss of hydrogen, increase in oxidation state, or loss of electrons. Okay, so that's what we mean by oxidation reduction. What do we mean by oxidation state? Oxidation state or oxidation number, you will hear me say oxidation state or number interchangeably. They're the same thing. Is the apparent number of electrons gained or lost by a species. Okay, so if a species has lost a certain number of electrons, we can assign it an oxidation state or a number. We are not saying that it has gained or lost these electrons. We're just saying that it may seem that way in order to balance things out. Okay, so now the next thing is you need to be able to calculate oxidation numbers and oxidation states or oxidation states. You also need to be able to identify if a reaction is a redox reaction. You should be able to identify identify reducing and oxidizing agents and all of these things. So it says distinguish between an oxidizing agent and a reducing agent in terms of electron gain or loss. I just said it. An oxidizing agent gives up electrons. Sorry, accepts electrons. And this is the tricky thing now. An oxidizing agent causes something else to be oxidized, and a reducing agent causes something else to be reduced. It is an agent of that. It's an agent of reducing. Okay, just like when you have change agents, you can have reducing and oxidizing agents. An agent of change is something that causes changes, right? So therefore, an oxidizing agent causes something to be oxidized, and a reducing agent causes something else to be reduced. How does it cause the thing to be oxidized? It has become itself reduced. That's why it is it causes oxidation. And a reducing agent causes something else to be reduced because it itself has become oxidized. So here, when it says distinguish between these two things in terms of that, let me see, I can text it. I'll write it in the form of a text. So an oxidizing agent that should be agent gains electrons right? So an oxidizing agent gains electrons while a reducing agent, this is supposed to be reducing, while a reducing agent accepts or gives up electrons. Reducing agent gives up electrons. Oxidizing agent, oxidizing. Oxidizing agent gains electrons while a reducing agent gives up electrons. That's what we're looking at. Okay, and that would be your 2 marks. You don't need to add anything else. All right. So the next bit. Next bit. It says Jaden carried out some tests and recorded observations in the table below. Lose the information in the table to answer the questions that follow. All right, so you have your test. An aqueous solution of C was added to acidified potassium manganate 7. Potassium manganate 7, or what you call potassium permanganate, is one of the most powerful oxidizing agents. Okay, and it will change from purple to colorless or purple to pink if it is reduced, because remember, the oxidizing agent is reduced. All right, next one now, an aqueous solution of C was added to a solution of potassium iodide. Potassium iodide solution changed from colorless to brown. All right, something is happening there. A strip of iron was placed, this is actually qualitative. A strip of iron was placed into an aqueous solution of copper 2 sulfate. All right, blue solution faded and brown deposits settled. Iron placed in copper 2. All right. A strip of silver was placed into an aqueous solution of copper 2 sulfate. Solution remained blue. Okay, so let's see what they're asking here now. State an oxidizing agent that is not mentioned in table 3. An oxidizing agent. Now, the most powerful oxidizing agents that you will come across, potassium permanganate, potassium or sodium dichromate. It could be potassium or sodium, whichever one, dichromate ion. Hydrogen peroxide is also an oxidizing agent, though it can be a reducing agent as well. And of course, chlorides, bromides, halides are all oxidizing agents, okay, because they will accept electrons. So that's simple. State one of those. Now, identify whether solution C is acting as an oxidizing or reducing agent in test 1 and 2. So look in test 1. It says solution C was added to potassium permanganate 7. Doesn't matter what you add to this thing, potassium permanganate, at this level. Potassium permanganate will always act as a reducing, as an oxidizing agent. Okay, so in test 1, solution C is acting as a reducing agent because it's coming up against potassium permanganate and it's not stronger than it. All right. In test 2, it says a solution was added to potassium iodide and you liberated iodine. Okay, how do I know iodine is produced? Because potassium iodide solution changed from colorless to brown. Once it changes from colorless to brown here, you know that this reaction is occurring, and I'll show you the reaction. What you have happening is that the iodide, which is bonded to potassium, right, is converted to iodine, which is aqueous. When you dissolve iodine in water, it looks brownish in color. So this iodide, and I'll get rid of the potassium to make it simple. This iodide is changing from an oxidation number of -1 to an oxidation number of 0. From -1 to 0 is an increase in oxidation number, since -1 is smaller than 0. And because of that, we know that it has been oxidized. If it has been oxidized, it must have been oxidized by an oxidizing agent. And in this case, the oxidizing agent is solution C. You have to interpret all of this from the information they give you. That's why you have to look at these things. So it is acting as an oxidant in another term for oxidizing agent in test 2, and then reductant in test 1, another name for reducing agent. Okay, so you may hear oxidant or reductant. All right, then now, let me see which page this is. Okay, it should be this page. Okay, so with reference to oxidation state, explain each of your answers. And so this now is where they're asking you to show the change in oxidation states. So in observation 1, let me see if I can spotlight this. In observation 1, the potassium permanganate changed from purple to pink. Now you would now need to remember this, that potassium permanganate is purple. And when it is purple, its oxidation number is 7. When it changes color to Mn+2, this is colorless or pink or colorless, whichever one. And that's what they're asking you for. So that's what you need to write, from Mn+7 to Mn+2. In the second situation, you would need to write that iodine change from I minus to I2. They didn't ask for the equation, I think. So therefore, you don't need to worry about putting in the electrons, but they could. Let me just double check. With reference, just the oxidation states, right? So it's just the oxidation states. So the manganese changed from +7 to +2, the iodine changed from -2 to 0, as you can see there. If a species is not bonded to another species, its oxidation number is 0. All right. So now moving on to the next question on this thing. Write an ionic equation with state symbols for the reaction which took place in test 3. So let's see what test 3 is. Test 3. A strip of iron was placed into the copper sulfate solution, and it says the blue solution faded and a brown deposit settled. All right, so they're asking us to write an ionic equation for that. So let's explain the observations first of all. So what you have happening is that you have copper sulfate solution, CuSO4. You place a piece of iron in it, right? Fe, let's just put Fe. And what's happening is that the blue color, this is blue, due to Cu2 plus ions. That's why it's blue. Copper 2 plus ions make things blue, all right? So they're saying the blue color is fading. If the blue color is fading, that can only mean one thing. The blue color is being removed from the solution. Then now it says brown deposits are settled. So what you're seeing at the bottom now, at the bottom of this thing, you're going to start seeing some brown deposits. What are those brown deposits? Well, the situation is that when you remember the reactivity series, this is why chemistry is difficult, and I say it to everyone. This question is not only pulling on your knowledge of redox reactions, it's pulling on your knowledge of qualitative analysis and metals and non-metals. Okay, so it is pulling on a lot of things. When you look at the reactivity series of metals, iron is above copper in the reactivity series. What does this mean? If iron is above copper in the reactivity series, it means that iron is more reactive than copper. And so therefore, iron will displace copper from solution. Okay, so what will have happening is that iron, which is a solid, when it combines with copper sulfate, which is aqueous, it will take the place of copper to form iron sulfate, aqueous, plus copper solid. So the brown solids you are seeing is the copper solid that is forming there. And the reason why the solution didn't, the blue faded, because the copper 2 plus ions are being converted to iron, to copper solid. Now, it would be very nice if your examiner asked you that, because it really would show your understanding of what is happening here. But that would be a very hard question for students. Okay, I would probably give that in an exam, but not CXC. Okay, so that's that. And that's 4 marks, you know. With reference, oh, sorry, I'm sorry. That's 2 marks. Write an ionic equation. I didn't write the ionic equation. So the ionic equation would be Fe solid plus Cu2 plus aqueous to produce Fe2 plus plus Cu solid. And I'm just gonna go to a thing there page now and show you an easy way of getting your ionic equation, the easy way of writing the ionic equation. So the easy way of writing your ionic equation, all right, I'll do this one. Fe solid plus Cu aqueous. You must have state symbols. If you don't have it, I can't help you. Okay, aqueous plus Cu solid. All you need to do is just identify the species which are aqueous on both sides. Iron is solid there. Iron is aqueous there. Copper is aqueous there. Copper is solid there. So the state changes. Sulfate is aqueous here. Sulfate is aqueous here. Cancel that because it's aqueous on both sides. Then now what you did not cancel, you rewrite. Plus Cu aqueous. Make sure you include the state symbols. Fe aqueous plus Cu solid. Okay. Now, if something is aqueous, it must have a charge. Must. Iron is solid, it doesn't have a charge. Copper is aqueous, so it must have a charge. What's the charge of copper? 2 plus. Iron is aqueous, so it must have a charge. Iron 2. Okay? If you put iron 3, depending on what they're asking you for the question, then, well, you can get the mark still. And of course, copper there is solid. So that's no charge. But once it's aqueous, it must have a charge. And notice what I did to write this ionic equation. All I did was just simply identify the species which are aqueous on both sides. The equation is balanced, and that's good. Even if the equation was not balanced, it does not matter. All you need to do is say, look, okay, is it aqueous on the left and aqueous on the right? Yes, cancel it. Is it aqueous on the left but solid on the right? Do not cancel it. And that's all. Okay, and that's how you write your ionic equation, given the information like that. All right. So now it says with, yes, somebody's asking. Yes. Question?
So I was just saying, okay.
Okay. Okay, that's good news then. With reference to the electrochemical series, explain the difference in observations between test 3 and 4. Yes, they did ask it. That's good. When was this? This must be a long time ago. 2016. That's not so long ago. Okay, so they're now asking with reference to the electrochemical series, explain the difference in test 3 and 4. So what is different about when you add iron to copper sulfate versus when you add silver to the copper sulfate? So I actually kind of explained this already, but let's do it again. Right? So in one instant, you have copper sulfate, CuSO4, and you place in that a piece of iron metal, iron. In the other case, you have copper sulfate, and inside of that, you place silver, Ag. Now, in this case, the iron displaced the copper, so it kicked it out. In this place, the copper did not displace the iron. So what is happening? Well, it is pretty straightforward. Iron is more reactive than copper. Silver is less reactive than copper. How do I know this? Because in the electrochemical series, iron is above copper and copper is above silver. Full stop. 4 marks. Okay, that's it. You don't need to add any decorations to your answer. We just want the facts, to be honest. We really just want the facts. People who mark your exams are my colleagues, really. And what they say really is that, and of course, their standards, they just want the facts because marking is very tiring. We don't want to be reading a whole lot of things and then it is wrong. It's better you just write the right answer and done. And we see the right answer and you get your full marks and it's over with. Okay? So that's what we're looking for when you guys are asking us these things, when we ask you these questions. Okay. So that's that. That was 2016. That was not so long ago, you know. Okay. It says electrolysis now. There was another redox question. Okay, we're going into electrochem. Okay, here we go. Here we go. All right, here we go. So, okay, that was just coming from this question. All right, that's coming from this question, but down here it asks you about electrolysis, not electrolysis, redox. So it says the reaction between iron and dichromate is considered a redox, reduction oxidation reaction. Define the term reduction in terms of electrons. We just did this. Reduction is the gain of electrons. Full stop. Do not add anything else, please. In the reaction, iron 2 acts as a reducing agent. Define the term reducing agent. Reducing agent is a species that causes another species to be reduced. okay, by giving electrons to that species. You can add that, but you don't have to. You can simply say a reducing agent is a species that causes another species to be reduced. Full stop. All right. Calculate the oxidation state of chromium in dichromate ion. So how do we do this now? Now there are rules governing this. This species is actually charged. Can't believe they put this on the exam. This species is actually charged. So the sum of the oxidation numbers, you're trying to find the oxidation number of chromium. So the sum of the oxidation numbers is equal to the charge. What's the charge? The charge is -2. How do I know it's -2? Well, it's right there. Okay. If it was, let's just say, MnO4 minus 1, then the charge would be -1. It's right there. Okay. So that's the charge on the species. The sum of the oxidation numbers is equal to the charge. So I need to add up the oxidation numbers of the chromium and the oxygen to get the answer, but I don't know chromium. How many chromiums are there? There are 2, so it's 2x. I can put Cr, but I'm just putting x, plus 7 times the oxidation number of oxygen. The oxidation number of oxygen is always -2. At your level, they do not talk about oxides and superoxides and peroxides. Sorry, peroxides and superoxides. They really just talk about oxides. And for oxides, the oxidation number is -2. So now, as you can see, this now becomes an algebraic expression. 2x plus 7 times -2 is equal to -2. So what is 7 times -2? That is -14. Is equal to -2. I might just carry it at the top there. So that now works out to be 2x minus 14, because in math, plus times a minus is a minus. 2x minus 14 is equal to -2. We're going to go up there now. So we need to get rid of the -14. So 2x is equal to -2 plus 14. In math, when you take a minus from the right side and carry it over to the left side, or right to left or left to right, whatever, it becomes positive. So now 2x is equal to -2 plus 14, which is equal to plus 12. 2x is equal to that. You need to find x. So x now is equal to 12 plus divided by 2 rather. X is equal to plus 6. Now, you will do that and you don't put the plus 6 and you lose 1 mark and you complain. Okay, because you think you got the answer right. Yeah, you got the 6, but it needs to be plus 6. Okay, so you must have the plus 6 to get the full marks. And you must show these calculations. It doesn't have to be this long. I just went through all of that instead of jumping steps. Okay, but it doesn't have to be that long, but you must show the calculation and you must put your plus 6, very critical. If you don't, it's going to be problems. All right, so the next question now. State 1 precaution that should be taken when carrying out the experiment. Of course, since you're working with oxidizing agents, you really should wear gloves. You really should wear eye protection on your lab coats. Those are straightforward things. And then that's that for that. The next part of our story now is that we want to look at electrochemistry. Okay. So we're going to start, rotate this. Yes, we did that. We start here. Good place to start. Now, electrochemistry, or electrolysis, as we often call it, right? Electrolysis is the breakdown of an electrolyte by the passage of an electric current through it. So there's a compound that we call an electrolyte. And if we pass an electric current through it, then the compound breaks down or it decomposes, and we call this process electrolysis. What is an electrolyte? An electrolyte is an aqueous or molten ionic compound, okay, or ionic species. It could be something else, but it's usually ionic in nature. Ionic meaning that it has a cation and an anion present. Okay, so your electrolyte is a molten or aqueous. Molten means that you take a solid, you heat it, and it changes to a liquid. So it must be in a liquid state. Aqueous means that it is dissolved in water. All right? So it's molten or aqueous. Okay? And you do your electrolysis in an electrolytic cell. Let me get a page. Okay, electrolysis is done in an electrolytic cell. So what does your electrolytic cell look like? Because you are working with liquids, it must have something to contain the liquid. So you must have a beaker. And since you're using electricity, you must have an electrode there and you must have an electrode there with your connecting wire, right? Positive side of the power source, negative side of the power source. This is positive, this is negative. The longer side is the positive side, the shorter side is the negative side. You can also insert a little bulb to show if current is flowing. And of course, you need to have your electrolyte. Okay, so that's your electrolyte. That's a beaker to contain the liquid. It could be something else. Now, this is called an electrode. Both of these are called electrodes. Now, because it is connected to the negative side of the power source, we call it the cathode. Okay, over here now, this is also an electrode, but it's connected to the positive side of the power source. So we call it the anode. This is connecting wire, which is like copper wire, right? This is your power source, which could be a battery or a cell or the outlet in the house. And this is a bulb or a lamp. And we call all of this our electrolytic cell. Okay, that's what we call it, our electrolytic cell. So that's your electrolyte and all your things. So what happens in the electrolytic cell now? In the electrolytic cell, you're going to have your cation and your anion separating. So you have your cation, which is positive, N plus, and you're going to have your anion, which is, let me just put AN minus. Now the anion is connected to the positive side of the power source. So the anions would move to the anode. Negative attracts positive. Okay, the cations is the cathode is attached to the negative side of the power source, so the cations would go to the cathode because positive attracts negative. So that's what would happen there. So the next question is, what happens at the electrodes? What happens there? At the electrodes, the cation would gain electrons to become neutral, and the anion would lose electrons to become neutral. So that's what happens there. This process of gaining and losing electrons is what we call discharge. Okay, it sounds weird, but that's what it's called, discharge, which means to lose your charge, really. All right, so cations would gain electrons, anions would lose electrons. Which ion, now in some electrolytes, you're going to have more than one cation and more than one anion. And they're going to be competing as to which loses their charge. What determines what loses their charge? There are a number of things. One, you have the electrochemical series. For the cations, it's really the electrochemical series, the position of the metal or the metal ion in the electrochemical series. For the anions, concentration can be one. Nature of the electrode is the other one, and the electrochemical series. If the electrolyte is concentrated, it will tell you if it is concentrated. That's how you know. In the question, it says, during the electrolysis of concentrated sodium chloride, you know it is concentrated because it says that. If the electrolyte is concentrated, then the anion of water, now water exists as two ions. I'm changing my color here. Water, no, that's not a good color. Yellow. Water, no. Black. Water, yes, there you go. Water exists as H plus ions and OH ions, right? This is the anion, this is the cation. Okay. Now the anion would go to the anode, the cation would go to the cathode, and we're looking at the anode right now. If the solution is concentrated, then the anion of the electrolyte will discharge. The anion of the electrolyte. So let's say the electrolyte was sodium chloride. Sodium is made up of sodium ion, which is the cation, and chloride, which is the anion. What we're saying is, if it is electrolysis of concentrated sodium chloride, the chloride would discharge, okay, to the OH. All right. For the cathode, the electrochemical series determines what is discharged. Okay. So therefore, that is the situation with it there. Now, if the anode is active, if the anode is active, then what would happen at the anode is that the metal which makes it up would dissolve in the electrolyte. Okay, so let's say you had as your electrolyte copper sulfate. When we just did this, that's why I'm using it. And this is iron, right? Because iron is more reactive than copper, the iron would dissolve in the solution, and the copper, the iron would dissolve in the solution here. So that's what would happen if it is active. The final situation is the electrochemical series. So the next situation is, if the electrolyte is dilute and the anode is not active, then the electrochemical series would determine what discharges at the electrodes. Okay, so that's what happens there in a nutshell for electrolysis. So let us go back to the questions now. All right, so here's the first question. Ethanoic acid is known to be an electrolyte. Define the term electrolyte. We just did that. An electrolyte is an ionic species, and they're going to say ethanoic acid is not ionic, but anyway, it is an ionic species in an aqueous or molten state. Okay? It really is ionic in nature. Hopefully they know that or not. Not know that. All right. Identify the ions that are produced from ethanoic acid during electrolysis. So for electrolysis of ethanoic acid now, we want to find the ions that are produced. This has to go back to your acids, bases, and salts, you know. All right. So when ethanoic acid, which is this CH3COOH, when it breaks down or it ionizes, you end up with the ethanoate ion and the hydrogen. So these are the two ions that they want, the ethanoate and the H+. Okay, that's what they're asking you for there. Then now it says you should define the term cathode. Define the term cathode. The cathode is the electrode which is connected to the negative side of the power source. That's one way of defining it. The cathode is the electrode where reduction occurs. That's another way of defining it. Okay, it is the electrode where reduction occurs, or it is the electrode connected to the negative side of the power source. Predict which ion from Ci above will migrate to the cathode. Of course, we know the anion, the cation would move to the cathode, which is the H+ ions. Okay, the cation moves to cathode. Is ethanoic acid a strong or weak electrolyte? Explain your answer. Now, this question, this one, really is coming from acids, bases, and salts. All right, acids, bases, and salts. So I will explain this. I'll use hydrochloric acid. HCl may be ionized to give that. Hydrogen ions and chloride ions. Ethanoic acid may be ionized reversibly. These are reversible arrows now. These are reversible arrows to give CH3COO minus plus H+. Okay, notice that both of them give protons and the ion, but look at the hydrochloric acid. The hydrochloric acid, the arrow goes in one direction. You see that? That means that all of the HCl here is converted to H+ and Cl minus. So if I had 100 molecules of HCl, every single molecule would be converted to that, H+ and Cl minus. Okay. Now, if I had 100 molecules of ethanoic acid, just some of it, so let's just say 30 molecules would be converted to that over there. And while the rest of it, which is 70, would remain as this. Okay. So it is what we call partial dissociation and full dissociation, or ionization. Let me use that term, ionization. In a strong acid, which is the same thing as a strong electrolyte. Okay, that's why I'm using the acid right now, because strong acid really is the same thing as electrolyte. In this context, in a strong electrolyte or strong acid, the ions, the species totally ionizes. In a weak electrolyte, this, like the ethanoic acid, the species partially ionizes. Not all of it is converted to ions. And that is why we say that ethanoic acid is considered to be a weak electrolyte. So you would say in answering this that ethanoic acid is a weak electrolyte because it partially ionizes. And then you would write this equation here to supplement your answer. That will give you your full marks. You heard what I said? So you say that ethanoic acid is a weak electrolyte because it partially ionizes. Full stop. Then you write the equation. Okay? And you get your full marks.
Yes, sir.
Okay. So we proceed. I think there's a question over on this side. That's 15 marks. Let's see what this is. Okay, that's organic. Sweet. Okay. A student conducted an experiment. Let's bring this in a bit. Conducted an experiment to determine the products formed when the electrolysis of aqueous copper sulfate using inert electrodes. That's good. In figure 1 shows are simplified. Figure 1 shows a simplified diagram of that. So there you have your battery, you have your ammeter. You don't do physics, so you probably know that's an ammeter. And an ammeter is used to measure current. You have P and you have Q. They don't tell you what is P, but we know P is connected to the positive side of the power source and Q is connected to the negative side. Invariably, they would ask you to identify what is P and what is Q, for sure. Okay, a current was passed through the electrolyte and the starting time was recorded. At 10-minute intervals for 1 hour, the volume of gas, oxygen gas evolved and the mass of copper deposited is measured. At the end of the reaction, the total mass of copper deposited was that. The volume of oxygen gas evolved is shown in the table. So you have that table there, the volume of, define the term electrolysis. Electrolysis is the breakdown of an electrolyte by the passage of an electric current through it. Okay, so it's a breakdown of an electrolyte by the passage of an electric current through it. Then now it says, suggest one material that could be used for the inert electrodes. Generally speaking, inert electrode is carbon or graphite, same thing. You can use carbon or graphite. Nobody's going to use platinum for this because platinum is too expensive and graphite could work. So graphite is fine. Using the data in table 1, plot a graph. And of course, I know you know how to plot a graph already. Draw a best fit line. The problem though is that sometimes you guys don't understand that a best fit line doesn't need to pass through any points at all. It just needs to match the trend. Okay? Just remember that your best fit line doesn't have to pass through any point. It just needs to match the trend of the data. Okay? So that's that. Use the graph to determine the time it took for 5.50 centimeters cube of oxygen gas to be liberated. So for you to do that, I'll show you how you do that now. They put up the scale for the graph already. So 5.50 centimeters cube. So you're going to find 5.5 centimeters cube on the graph. You find 5.5, which is right here, right? You draw a line from 5.55, go right across. It's going to split your graph somewhere. Let me look at the numbers and I'll tell you, I'll give you an estimate of what the graph should look like. Okay, let me see. 2, 4, 6, 7, 8. Okay, so it's going up. All right, so your graph should look something like this. Not exactly like it, but should look something like it. As the time increases, the volume of CO2 increases, so your graph should look something like this. Okay, something like that. So all you need to do now is for the 5.5, you draw your line across. I'm not going to redraw the line. Just going to bring this down. Wait, bring it up. Right there. And then where it cuts the graph, you draw a line down. Okay. So it cuts the graph right there. You draw a line down. This would be a straight line. Of course, I'm not using a ruler. So, and then that would give you the time it took to produce that amount of, see it right there? So it would basically, this is saying 35 minutes. That would give you the time it took to produce that amount. Okay, we know how to do this interpolation already. All right, good. So that would be straightforward. Identify all the ions present in the electrolytes used in the experiment. So you need to now be able to identify the ions present. So what you need to do, first of all, is write down the electrolyte. The electrolyte is copper sulfate. Copper sulfate is made up of copper ions and sulfate ions. However, it is aqueous copper sulfate, which means that it also contains the ions of water, because aqueous means water. So it would contain H plus ions and OH ions. And that is what you need to write. These two over here and the OH and the H plus ions to get your full 2 marks. Okay. Of course, I did mention that they would say this now. P and Q are electrodes shown in the apparatus used for the electrolysis in figure 1. State which electrode is the anode and which is the cathode. So you go back up. All right. P, I think, was connected to the positive side of the power source. This is far. Yes, P was connected to the positive side. And so remember that the anode is connected to the positive side. And once you know that, you know what the cathode is. So P is the anode and Q is the cathode. And that would be the answer for, where is that? That would be the answer for this one right there. State one ion in the electrolyte that will drift towards the anode. Of course, the anions would go to the anode, and that would be the sulfate and the OH. Write an ionic equation for the reaction taking place at the cathode. Remember now, at the cathode, the electrochemical series determines the discharge. The electrochemical series determines what discharges. Okay, so I'll show you now. You should be seeing a blank screen, right? Yes?
Yes, sir.
Well, you're seeing like, we call this now? Google, right?
Yes, sir.
All right, so here you go. There it is. So this is the electrochemical series. Yeah, let's just use this. Now notice here that in this electrochemical series, hydrogen is above copper. There you go, hydrogen is above copper, which means that if you have hydrogen and copper, the copper will discharge. The one which is lower down will discharge in this series here. Over here, you have the one which is lower down will also discharge in this series as well. OH is at the bottom. Then you have chloride, and look where sulfate is. Sulfate is almost at the top, okay? And OH is at the bottom. So OH would discharge, and the copper would discharge. So let's go back to the question. The question says now, write an ionic equation for the reaction taking place at the cathode. So we know that we have copper and hydrogen. The copper would discharge. So let us write an equation for that. For that, we would have Cu2 plus 2 electrons to produce Cu solid. And this is aqueous. And that's your equation. It must be balanced and it must have the state symbols. It must have the electrons. Okay, this is balanced. And by balance, we mean that the number of each atom on both sides is the same and the charge is the same on both sides. On this side, I have one copper. Over here, the charge is 0. Over here, the charge is also 0 because this is +2 plus -2. And +2 plus -2 is 0. That's equal to 0. So the charge on both sides is actually equal. Okay? So that's that bit. Give me 1 second. Okay, so the next, are we still there?
Yes, sir.
Okay. The next part of the question really focuses on quantitative electrolysis. All right, so let's explain quantitative electrolysis first. This guy called Michael Faraday, some time ago, he found out that there was a way to determine how much, that's what quantitative means, how much. He found a way to determine how much product you could get at the cathode or the anode, okay? Based on the amount of current flowing through the circuit, you could find out how much product you got. So he basically said that the amount of product you get, which we can consider a mass, is proportional to the charge that is flowing through the circuit. So the mass is proportional to the charge. So if the charge increases, the amount you get should increase, right? Which is what we kind of just saw in the graph. Then now he said there's a way we could calculate the charge. Q is equal to current times time. This is current and this is time, all right? So Q is equal to current times time. Q is it, as somebody says. Q is equal to IT. So that is how you find the charge. The charge is the amount of electricity flowing through the circuit. He also found, very importantly, that 1 mole of electrons, for you to add 1 mole of electrons to a species, or for you to remove 1 mole of electrons from a species, it requires 96,500 coulombs. Really, it's about 96,485 coulombs, but it will be rounded off to 96,500. But your examiner may say that you should take it as 96,000. If they say take it as 96,000, you use 96,000. Don't use 96,500, okay? Because that would mean you're not following instructions. So these three things.
Give me 1 minute, please.
What's that?
Give me 1 minute.
Sorry, you're breaking up a little.
I'm saying, give me 1 minute.
Oh, okay. You're back?
Yes, sir.
Okay. So these are the three critical things that Michael Faraday found. The amount of product is proportional to the charge Q. Q, the charge, is the amount of current that is flowing through the circuit. We can calculate that by using Q is equal to IT, where I is the current, T is the time in seconds, Q is the charge in coulombs. 1 mole, he also found that for me to add 1 mole of electrons to a species, or for me to take 1 mole of electrons from a species, it's going to require 96,500 coulombs of electricity. Okay, so those are the things that he found. And these are the things that we'll be using to do all our calculations. So bear that in mind. So here we go. First question. Calculate the quantity of electricity that passed through the copper 2 sulfate solution when 3 amperes flowed for 1 hour. And this is pretty straightforward. Notice here they say 1 Faraday is 96,500 coulombs. So you're trying to find the quantity of electricity. They gave the equation. What on earth is this? So the quantity of electricity is Q is equal to IT, and they have actually given the equation. So that's going to be equal to the current 3.5 A times time, which is 1 hour, but it needs to be in seconds. So it's 1 times 60 minutes times 60 seconds. Okay, I guess that's what they're really testing you on. And that works out to be 3.5 times 60 times 60. That is 12,600 coulombs. So you'd get seconds, ampere seconds, which is the same thing as coulombs. Okay, so that's that. On to our next question. Our next question now says, calculate the moles of copper deposited. Let me see what was the thing there for this. Okay, the question actually gave the mass of copper deposited. So I have to go all the way back up to the top to get that. Okay, so it was 5.50 centimeters cube of ox. No, that's not that. Here we go. 4.85 grams of copper. That is the amount of copper that was deposited. So I'll go all the way back down here now to calculate the moles of copper. 4.85, even if I get it wrong. 4.85. So calculate the moles of copper now. And as I said earlier, moles is in application to questions. So it's not about, it's not that you're gonna see moles and be like, okay, they're gonna give you a mole concept by itself necessarily. So moles is equal to mass divided by molar mass, and the mass was 4.85 if I remember correctly, divided by the molar mass of copper, which is 64 grams per mole. You do the math, you get the answer there. Okay, that's 3 marks. So that should be straightforward. Use your calculator. Calculate the mass of copper deposited given that the relative atomic mass of copper is 64. Okay. Okay, so we just calculated the moles of copper deposited, right? And that was from a mass. I'm not sure about this question. It's pretty strange. Calculate the mass of copper deposited given that the relative atomic mass of copper is 64. We just they gave us the mass of copper deposited, unless it's a different question. But we just calculated that, so we're not going to look at that. All right. State one reason for the difference in mass of copper calculated in that and the mass measured by the student. Oh. Okay, so just one reason why the difference there's a difference in mass of copper calculated in that and the mass measured in by the student, 4.85. So there's a difference because you're going to have, your reaction is not being done under, let's just say, ideal conditions, right? And because it's not being done under ideal conditions, you would end up with errors. There's going to be mass losses, for example. When you're transferring stuff, some of the copper might be left on the paper, some might be blowing away, a number of things may happen. So therefore you won't get the same amount as in under ideal conditions, okay? And that's the situation with that one. State the color change that would have taken place in the electrolyte after a few hours. Well, remember we have mentioned this already that copper 2 sulfate or copper 2 is actually blue. So if the solution is losing copper 2 plus ions, then the solution is going to get paler and paler and paler. After a few hours, it might look colorless, might. Okay, but it's going to lose the blue color. The student was asked to use the same electrolyte to purify a piece of impure copper. State how the electrodes in figure 1 on page 5 can be modified to obtain pure copper from impure copper. So let us just pause here and give a little bit of notes. One of the uses of electrolysis is electropurification. In other words, you can purify substances using an electrolytic cell. How do you do that? The substance that you want to purify, you place it at the anode. At the anode. Okay? So in this case, we want to purify copper. We're going to place the impure copper at the anode. The copper is going to dissolve in the solution and then get deposited at the cathode. And the impurities would fall to the ground. So in other words, let me show you what I'm talking about. So this is your electrolyte. This is your cathode. That's your anode. This anode is going to be impure copper. You were saying something? Would be impure copper, right? And then of course your electrolyte is copper sulfate. So what would happen is that the copper here would dissolve in the electrolyte. So it would change from Cu solid to Cu2 plus. Okay, so the solution would get a more intense blue. But then the copper, which is dissolved in the electrolyte, would then go to the cathode and become Cu2 plus, from Cu2 plus to Cu solid. And so therefore that is what would be happening. The impurities in the copper now would be found at the bottom of the thing. So they would be down here. And that's how you would purify your impure metal. If you want to electroplate something, let's say you have a watch and the watch is made out of bronze, but you want people to think that you have a gold watch. You would put your watch at the cathode instead of the anode. So that's a big difference. For purification, the substance is placed at the anode. For electroplating, the substance is placed at the cathode. So you'd put your watch at the cathode and then you would allow the gold to deposit on it. All right. So those are two applications of electroplating. So for this question now, what they're asking you for is state how the electrode would be modified. What would happen is that the cathode would become, the anode would be impure copper and the cathode would be pure copper. And that's what they're really asking you to state. Calculate the number of moles of iron in the iron. Okay, nope. Okay, so we go back up a bit. Think we did this already. We did that already. Okay, so we did all of that already. Let's look at this page. Okay, so let's look at this page. This is multiple choice, right? The Faraday constant will liberate 27 grams of aluminum and 24 grams of magnesium. So the Faraday constant is 96,500 coulombs. 1 mole of electrons is equal to 96,500 coulombs. Okay, and For example, for magnesium, Mg2 plus 2 electrons to produce Mg solid, right? If you're given a question like that, all you need to do is look at the equation and say, how many electrons are involved in this equation? And that is 2. See it right there? 2 electrons. Okay. Now, how many? Faraday says that for 1 mole of electrons, it's 96,500 coulombs. In this equation, I have 2. So it would mean that for this equation to occur, I'm going to need 2 times 96,500, which is 193,000 coulombs. This 193,000 coulombs actually produces 1 mole of magnesium. Okay, that 1 mole of magnesium has a mass of 24 grams. Okay, so 193,000 coulombs produces 24 grams of magnesium. So it would mean that A is incorrect because it's saying that the Faraday constant will release 24 grams of magnesium. The Faraday constant would not release that. It would be half a Faraday that would do that. Okay. So look at the second one, 27 grams of aluminum and 12 grams of magnesium. The 12 grams is fine because half a Faraday would produce 12 grams since 193, since 2 Faradays is equal to 24 grams, then 1 Faraday would be equal to 12 grams. So this 12 grams is fine, but this is not fine because aluminum is Al3 plus. Okay, aluminum is Al3 plus, plus 3 electrons to produce Al. And that is 3. So it would be 3 Faradays would be equal to 27 grams. Because aluminum has a molar mass of 27 grams. And they're saying 1 Faraday. So that's not right either. So question B, part B would not be right. Let's look at C. 1 Faraday would produce 13.5 grams of aluminum. That is also not right. Because 1 Faraday, 3 Faradays would produce 27 grams. And therefore, half of that is 13.5. So it would be 1.5 would produce 13.5. Okay. For the last one now, it says 9 grams of aluminum and 12 grams of magnesium. So let's look at that one. For that one now, we can safely say that 3 Faradays would produce 27 grams of magnesium. Therefore, 1 Faraday would produce 9 grams. 27 divided by 3. 3 9s 27, right? 2 Faradays would produce 24 grams of magnesium, but 1 Faraday would produce 12 grams. So see, 1 produces 9, 1 produces 12. So our answer there is D. This is an interesting multiple choice. This is not actually CSEC question, but the thing about it is it forces you to think about what you're actually doing, right? And come up with a proper answer. Okay. Am I talking to myself? All right. Let's see if there was another readout. All right, so you should be seeing on the screen now something which talks about electrolysis, right?
Yes, sir.
All right, we're just gonna go through one more of this, then we're gonna move on to acids, bases, and salts next, okay? So the process of electrolysis has a number of useful applications during the purification of copper by electrolysis. We just looked at that. Special electrodes are used to give the desired products. Define the term electrolysis. Electrolysis is a breakdown of an electrolyte by the passage of an electric current through it. All right. The examiner is looking for some terms. Breakdown, electrolyte, passing of electric current through it. Those 3 things are critical. If you don't have them, chances are you won't get a mark. State the type of anode that is used in the purification of copper. Notice that in this question, they're asking you for it. So in the purification of copper, it's going to be impure copper. That's the anode, impure copper. Figure 2 depicts the apparatus that is used to electrolyze a sample of molten lead iodide. Remember I said lead bromide. Remember I said molten means that you take a solid and you heat it and then it melts, right? So that's what's happening here. It says which of the electrodes, electrode 1 or 2, is what? In the diagram is the cathode. Okay, sorry. Of course, electrode 2, because electrode 2 is connected to the negative side of the power source. The cathode is connected to the negative side of the power source. Generally speaking, the cathode is on the right as well, generally speaking, but don't just say, okay, the cathode is on the right and say cathode. Look what it's connected to, okay? Write the formula of the ion that migrates towards the anode. So anions go to the anode. And we are looking at molten lead bromide. So therefore, bromine would go to the anode. So it's Br minus, okay? Next thing, says write a balanced ionic equation for the reaction occurring at the cathode. Lead would go to the cathode, so therefore lead would gain 2 electrons. Lead is 2 plus 2 electrons, and this is liquid now to produce PB solid. Your examiner is looking, I can guarantee you, they're looking for whether or not you put this as aqueous. If you make it aqueous, you are saying to the examiner that it is dissolved in water, and that's not the case. The question said molten lead bromide. When you melt something, you do not add water to it. You simply heat it until it changes from a solid to a liquid. Okay, so lead bromide, molten here is going to be liquid, not aqueous. So you have to be very careful of that. They will look for it so that they can take off that mark. That will separate goat from sheep. It says a current of 5 amperes is passed through the molten lead bromide for 5 minutes. Calculate the mass of lead that would be deposited. RAM of lead is that. Faraday's constant is 96,500 coulombs. So first thing you need to do here is calculate Q is equal to IT. So Q is equal to IT, and the time, the current was 5 amperes. The time, 5 minutes. 5 minutes, but time must mean seconds. So it's 5 times 60 seconds. And this is all seconds. And that works out to be, you should have your calculator, remember. So it's 5 times 5 times 60. And that works out to be 1,500. 1,500 ampere seconds or coulombs. Okay, but that's not what they're asking us for. They're asking us to calculate the mass of lead that would be deposited in this time. So how do we, yes, go ahead.
I'm not seeing seconds in the what is the statement? So how do we know, sir, that you convert from minutes to seconds?
Okay, let me clear right here, because this is where it's done, right? So we know it should be in seconds. So what I did was, since it's 5 minutes, see it right there, you can still see it. We say, sorry, the time is 5 minutes, and to convert minutes to seconds, we multiply by 60. Then we put that in bracket and put the seconds right there.
Yes, sir, I understand that, but I'm saying I'm not seeing seconds in the statement. So I'm wondering if it is in minutes, then we convert to second.
Yes, definitely. I get you know. You definitely have to convert to seconds.
Yes, sir.
And if they give you days, you have to convert days to seconds. Okay, so that is 1,500 coulombs, right? Now they're saying calculate the mass of lead that would be deposited. So basically they're saying if you run a current of 5 amperes for 5 minutes, which equates to a charge of 1,500 coulombs, how much lead would this deposit? That is what the question is asking you. How are you going to work that? Here's what you do. You have the equation for lead. Let me actually undo that. You have the equation for lead right there. Lead 2 plus 2 electrons to produce PB solid, right? So you need to examine the equation. How many electrons are involved in this equation? Well, 2, because it says it right there, 2 electrons. What's the charge for moving 2 electrons? Well, Faraday said that 1 mole of electrons is equal to 96,500 coulombs. And I have 2 moles of electrons. So it's going to be equal to 2 times 96,500, which is 193,000 coulombs. Okay? That's what it's going to be equal to. Now you ask yourself the question, how much lead was formed in this reaction? Well, the statement said 1 mole of lead. See it right there. 1 mole of lead. You now say to yourself, what is the mass of 1 mole of lead? Well, the question actually gave it. See it right there. The relative atomic mass of lead is 207. So you would actually write a statement now which looks like this. 193,000 coulombs is equal to 207 grams of lead. Right? But the question is saying, if 1,500 coulombs was being run, how much lead would this produce? So you would now say 1,500 coulombs is equal to X, and then you cross multiply. Right? And then you work that out, you get your answer. X is equal to 1,500 coulombs times 207 divided by 193,000 coulombs. And you need to cancel your coulombs to get your grams, and then you get your answer. Okay, 4 marks. Examiner is not just going to give you 4 marks for doing nothing. You have to do all of these calculations. Okay, so that would be that bit.
Sure. For questions where you want to use relative atomic mass, they're going to always give it to you?
Yeah, in today's exam, they give you guys. When I was doing it, they didn't give us. You had to know it.
Oh, okay.
But that doesn't mean that every time they give you, you need it. What they will do sometimes is they will put it there and you don't really need it. So you need to determine if you need it or not. Okay?
Yes, sir.
All right, so we will proceed now to the next question. It says 2 experiments were set up as shown below. It's a bit obscure, but let's see. You have zinc rods that is placed in magnesium sulfate and zinc rods that is placed in copper sulfate. It says in experiment 1, the zinc rod is immersed in, okay. In experiment 1, no visible change was observed, while in experiment 2, a brown solid settled to the bottom of the container. Explain the observations from both experiments. We actually did this since morning, if you recall. This has to do with the reactivity series. With the reactivity series, magnesium is above zinc. So zinc cannot displace magnesium from a species. Okay, but copper is below zinc, so zinc can displace copper. When zinc displaces copper, the solution is going to lose its blue color and the copper solid is going to deposit at the bottom of the container, which is why you saw the brown stuff. It should say brown somewhere there. See, brown solid settled at the bottom of the container. Okay. That was 2014. And of course, that's for experiment 2. All right, this would be our last one, and then we're going to move on to acids, bases, and salts. So figure 4 shows a simplified diagram of a cell using the electrolysis of molten sodium chloride. This is molten sodium chloride. So molten means no water present. You have your source of current, your cathode, your anode, your molten sodium chloride. Why is molten sodium chloride rather than solid sodium chloride used as the electrolyte? This is like checking if you really understand what you're doing. First things first, solid sodium chloride cannot conduct electricity because the ions are bonded together. They're trapped together, so they can't move. And so therefore, it will not conduct electricity. Molten sodium chloride is used because it is an electrolyte. The ions are free to move. And so because the ions are free to move, they can move to the electrodes to produce sodium and chlorine. And that's what they're looking for. I don't know why it's 3 marks, but anyway. Write ionic equations for reactions occurring at each electrode. Of course, sodium goes to the cathode and chlorine goes to the anode. So you have sodium, which is liquid, it's molten, plus 1 electron to give you sodium solid. Then you have chlorine, Cl minus 2. This is liquid to produce Cl2 gas plus 2 electrons. Okay, and that's that. Then now it says calculate the quantity of sodium which will be deposited when 10 amperes of current are passed through the electrolyte for 2 hours. So now they give you 2 hours here. That's a stretch. So anyway, you do the same thing again. Same thing again. We just wrote the equation, so we don't need to get back into that. So you need to work out Q is equal to IT first. Q is equal to IT. Q is equal to I times T, which is equal to current. 10 times time. It was 2 hours. So how we convert 2 hours to seconds now? 2 times 60 minutes times 60 seconds. And we get our answer for that, which is 10 times 2 times 60 times 60. That works out to be 72,000 coulombs. So what we have happening is that there is 72,000 coulombs that is pouring through the cell. We know that 96,500 coulombs is equal to 23 grams of sodium. If you don't know how I get that, tell me. Okay. And so 72,000 coulombs is equal to X, and you cross multiply and you get the value of X and you get your answer. Okay. And that's that. State 2 uses to which the chlorine generated in figure 4 can be put. In other words, what do we use chlorine for? This is nice stuff. Chlorine is used in bleach, don't it? Chlorine is used for cleaning pools. Chlorine is used for disinfecting water. So you can say any of those things. How does the product of the electrolysis of molten sodium chloride differ from that of brine? With brine, you get sodium hydroxide being formed. That's one thing. Sodium hydroxide is going to be formed, and you're going to get some oxygen being formed as well at the anode. Explain why during the electrolysis of brine, the electrolytic solution gradually becomes basic. And I actually just mentioned sodium hydroxide. Sodium hydroxide is being formed. And so because sodium hydroxide is being formed, sodium hydroxide is a base. So therefore, it would become basic because of that. Okay, so that is electrolysis, electrochemistry. We're going to move on now. This would be the last thing that we do before our break. We're going to move on now to acids, bases, and salts. Acids, bases, and salts. Okay, let me find those questions. So while I'm looking for that, let me explain acids, bases, and salts for you. So generally speaking, you are expected to know a few things about acids, bases, and salts. One, you need to know to define an acid, base, alkali, salt. So let's begin with the definitions. What is an acid? An acid is a proton donor, or an acid is a substance that produces protons in solution. Okay? Those things kind of mean the same thing, really. All right. An acid, and so that's an acid. A base is a proton acceptor, or a base is a substance that produces OH ions in solution. All right. Following so far? You guys still there?
Yes, sir.
CSEC KBS. Here we go. Okay, good. Okay, so the next thing we want to define is a salt. A salt. I tend to define a salt in more in the sense of what happens for a salt to form. So a salt is formed when the hydrogen in an acid is replaced by a metal or the ammonium ion. So let's see what we're saying by that. All we're simply saying is that if you have an acid, HCl, right, and you replace that with a metal such as sodium, you're going to get sodium chloride, and that's a salt. If you replace it with NH4, you're going to get ammonium chloride, which is also a salt. All right. So if you have sulfuric acid, H2SO4, and you replace the hydrogen with sodium, you're going to get sodium sulfate, and that's a salt. All right. If you replace it with NH4, 2SO4, you're going to get a salt as well. So once you replace the hydrogen in an acid with a metal or the ammonium ion, you get a salt. Now, how can I tell the difference between an acid and a salt, a base, an acid and a base? An acid turns blue litmus paper red. A base turns litmus paper blue, okay? An acid is corrosive, it will burn you. Bases are not necessarily corrosive, but alkalis are corrosive, and I'm going to talk about alkalis soon. Acids conduct electricity in an aqueous solution, okay? So sulfuric acid, that's why they use sulfuric acid in batteries, because it will conduct electricity. Acids have a sour taste, like vinegar. Vinegar is an acid, or lemons. Lemons contain acid. That's why they have such a sour taste. Citrus fruits, those things. Bases have a bitter taste. Bases are slippery to touch. So soap is made from bases. You take a base and you put it in some oil, heat it, and you get soap. Okay. Well, alkali really, not a base necessarily. So they're corrosive and all that. They have a pH, acids have a pH of less than 7, bases have a pH of greater than 7. Of course, 7 is the neutral. All right. Now, alkalis are bases that dissolve in water. It's easy to identify an alkali because they have OH. They're bonded to metals and they have OH, like sodium hydroxide. That's an alkali. Magnesium hydroxide, calcium hydroxide, ammonium hydroxide. Those are all alkalis because they have the OH there. Okay, so then now the situation is, what do acids react with? Acids react with bases. When an acid reacts with a base, what do you get? Salt and water. Acids react with metals, reactive metals. When an acid reacts with a metal, what do you get? Salt and hydrogen gas. When an acid reacts with a carbonate, what do you get? Or a hydrogen carbonate, you get a salt, water, and carbon dioxide. Okay, acids will also react with sulfites, SO3 2- ions. And when it does with that, you're going to get salt, water, and sulfur dioxide. You'll realize that every single reaction of an acid gives you a salt. Okay, all of them give you a salt. Give me a second. All right, so Those are the reactions of acids. Then now, what do bases react with? Well, bases react with acids to produce a salt and water. Bases also react, well, alkalis, and this is the one reaction that is pretty serious. Alkalis react with ammonium salts. So NH4Cl, see, ammonium plus something like a sodium hydroxide to give you a salt, NaCl, plus water, plus ammonia. This is the one reaction that we say, look, you know that bases react with acids, but do you know that bases or alkalis rather react with ammonium salts to give a salt, water, and ammonia? You must know this reaction. Okay, it's pretty common. All right, so now that's that. Then now, for acids, bases, and salts as well, you need to know about oxides. Oxides, all right? So there are actually 4 different types of oxides. You have acidic, did I say 4? Yes, acidic, basic, neutral, and amphoteric, okay? Let's look at acidic oxides first. Acidic oxides are oxides of non-metals. In other words, it's oxygen bonded to a non-metal. So non-metals such as nitrogen bonded to oxygen, sulfur bonded to oxygen, right? Carbon bonded to oxygen, nitrogen, well, we have nitrogen already, bonded to oxygen. All of those elements have oxygen bonded to a non-metal. Now, what's special about these oxides is that they're called, they're acidic oxides. They're called acid anhydrides. Acid anhydrides. So what happens is when they dissolve in water, so if I were to take sulfur trioxide, SO3, and I put that in water, what I'm going to get is sulfuric acid. So these oxides dissolve in water to give you an acid. So that's why they're called acidic oxides, because they dissolve in water to give an acid. The next type of oxides are basic oxides. These are oxides of metals. So sodium oxide, magnesium oxide, aluminum oxide. No, let's not do aluminum. Calcium oxide, right? These are oxides of metals, and these are bases. These are oxides of metals that react with acids to give you salt and water. So if they react with acids to give you salt and water, they are base. So these are oxides of metals that are bases. The next type of oxides I mentioned was neutral oxides. These are oxides that do not have, they have a pH of 7. For example, carbon monoxide and the very famous H2O has a pH of 7. Okay, water that is. So these oxides have a pH of 7. The next type of oxides would be the amphoteric oxides. Ampho means dual in nature in this context. So these are oxides of zinc, aluminum, and lead. What's so special about them? Well, the oxides of these 3 metals, they can react with both acids and bases to give you a salt and water. Okay, so they will react with both acids and bases to give you a salt and water. All right, so now, next thing now about acids, bases, and salt that you need to know is salt preparation. How do I make salts? How do I make salts? And I have a little graphic here. Let's see if I can find it very quickly.